I don't think I deserve all this. It's a pleasure. I'm actually deeply honored and humbled to be here. As a child, I used to read articles by Dr. Narasimhaya in Illustrated Weekly of India about various things going around in Bangalore and around Bangalore in the country. So I'm really honored to be here. So what I will do is I will share some of my thoughts on what exactly how signal processing is affecting our daily lives in some sense, and maybe share with you a few experiments which we have carried out in IISc to build small systems. We have not built any complicated systems, but where signal processing concepts are being used. So let's maybe start with signal processing for Ubiquitous MIMO systems. So I'll explain to you what is MIMO. It is multiple input, multiple output system. And so we'll see what happens and what each term means. So signal processing, I think all of you are familiar. We are basically doing signal processing without even knowing that we are doing signal processing. So as every field has, it has a theory and it has things which use the theory to build things or interpret things or understand things. So if you look at the theory, signal processing theory deals with representing signals in a certain way. Okay? So you can represent it in a visual manner. So let us say this is actually a two-dimensional signal, black and white. And the intensity of this light is actually a signal which is impinging upon our eyes and then our brain interprets it. So representing a signal can happen in a visual form, can happen by drawings, or it can happen in any other way. The other way, of course, is to invoke mathematics. So most of the theory is built on sound mathematical principles. So we represent signals in mathematics, mathematical tools. And then processing is basically to manipulate these equations in mathematics. So let's say you take a Fourier transform or something like that. That is a signal processing. Okay? And then finally, after doing this manipulation of various representations, we finally have to interpret it. If you do not interpret what comes out after the processing and manipulation, it is of no use to us. Okay? So the theory will sort of tell us that we need to have a representation model, a processing and manipulation model, and an interpretation of what comes out after all these steps. And that helps us build intelligent and smart systems. So signal processing systems will basically consist of sensors and transducers, algorithms which will try and manipulate these things. And then you have software and hardware implementation of these algorithms. So this is basically part of the signal processing system. So now all of us have been exposed to typically a signal processing system right from the day we are born, because we ourselves are a signal processing system. Human beings are signal processing systems. So we'll come to that once I define the other. So if you look at a signal processing system, you have, let's say, a physical parameter or phenomenon, and then there is a sensor or a transducer which converts this physical parameter phenomenon into a signal input, and then you process, you get a signal output, and you say sensor transducer. So let's start with the system what I am actually using now, right? I am speaking, and this microphone is a sensor or a transducer, correct? So this microphone is able to respond to the acoustic pressure and convert that signal into an electrical signal. So you have an electrical signal. And this electrical signal is then processed, basically amplification. And then, of course, here there is a wireless communication channel, but let's assume that do all that, there is a signal, and then it goes to the speakers. And the loudspeaker is able to convert this electrical signal back to an acoustic sound wave, which we are able to listen and perceive. So this is an example of a simple signal processing system. Now there are many more complicated systems which are available. So what is a multiple input, multiple output system? So this is the most general form of a system where you will have multiple inputs and then there is a box which uses all these multiple inputs and gives out multiple outputs. Okay? So just like we as a human being, natural systems, we are multiple input, multiple output systems because we are able to receive signals from using our eyes, using our ears, and we are able to process it using our brain and then give out output which are responding to the situation, right? So it's a natural system. So animals, birds, all of them are actually natural MIMO system. So a single input, single output system which we usually study in signal processing theory in an engineering course is a subset or is a special case of a multiple input, multiple output system. So what I will do now is try to present to you a few MIMO systems which we are familiar with and which we can use, and then see how certain things, signal processing, where signal processing plays a role in understanding maybe physics phenomena and maybe discoveries. So let's start from, like all our ancestors, we always like to see what is happening in the skies. And so let us consider this example of a radio telescope. Okay. Now a radio telescope, this is how it looks. This is just one example of a radio telescope in giant meter wave radio telescope in Pune. Near Pune you have the giant meter wave radio telescope. So it has a lot of dishes. And then they are spaced in a sort of a Y-shaped array, spanning several tens of kilometers. Okay. Now this telescope is actually pointing towards the sky and trying to receive signals coming from pulsars. So this signal which is being generated by a pulsar is actually received by this array. So there are multiple antennas that you see, and these dish antennas are trying to receive this signal. Now what exactly happens to a signal which is being radiated in outer space? By the time it comes to this telescope, it is a very, very weak signal. Okay? Just like a signal, if somebody is talking outside this building, we will not be able to hear it properly because the sensitivity of our ear cannot decipher what is happening. But the sound wave is still there. There is a signal coming into our ears, but we are not able to process it because our sensitivity levels are low. So, if the signal is very weak, how do I extract this signal from whatever source of information? So, the first thing is that this dish is basically a collection, basically collects. We are all familiar with dish. We have dish TVs and dish antennas for our TV channels. So this will collect the signal, and because there is a parabolic kind of a reflector, remember this is not a solid dish because of the wavelengths. You actually have a mesh here, just a mesh, and that mesh sort of reflects, and this is the collection point. And there the signal is sort of received at a very, very low level. And that is then, using amplification, is sent to a central station. Now, receiving a signal from one antenna will not tell us where it is coming from, except that you know that there is a signal. But if you want to know where exactly it is coming from, then you need multiple antennas to look at that point and then find out where the position of that pulsar is. And then you need to do what is the frequency of this pulsar. This pulsar is rotating, so you need to know what is the frequency of this pulsar. So signal processing will enter this system, and because we are using multiple inputs, so you can classify it as a multiple input, multiple output system. So staying back in the skies, our navigation system is a multiple input, multiple output system. the GPS which we use on our smartphone, now the new Indian Regional National Navigation Satellite System, IRNSS, is also a MIMO navigation system, where you have satellite signals which are received by a receiver, which could be a smartphone, and using multiple satellites and finding the range of each one of those satellite systems. Because the satellites will transmit a signal, you will receive the signal, you will try to find your range with respect to each of these satellites, and using the principles of triangulation and etc., you will be able to find your position with reasonable accuracy. Now, the accuracy will depend upon how well you can estimate the range of yourself or your device to the satellite system. And there are so many other factors which happen in the ionosphere and other noisy systems. So signal processing is used trying to estimate the best possible estimate of your range. So you have multiple navigation satellites, and then you have position and velocity which comes out of it. So this also is in some sense a MIMO navigation. We all would have taken a flight at some point in time. If you have not, then these radars are useful. So you would have seen these radar signals, which are radar systems at airports and other places, where you would like to find the location of incoming aircraft, right? So in a civilian scenario, you will have a radar which generates a signal which has a beam, and this signal goes and sort of impinges upon a target. I have used a fighter plane just for my next example, but this could be a civilian plane at an airport. So you will receive this echo of the signal back, okay? And when you receive this signal, you process it and you want to find a detection. So this is a cartoon representation. So this is a pulse which is sent out by the radar. It goes, gets reflected, comes back, and you will receive a sort of a signal. This is a nice, very strong signal. Typically they are very, very weak signals. I just use as a cartoon. So the distance between this pulse and this occurrence of this will tell us how much is the time duration of the echo will tell us how far the target is. Okay, so that is how you find out. Now, in an enemy aircraft scenario, suppose this is your target, and we are trying to find where the enemy aircraft is. So what the enemy does is, it tries to fly another aircraft using a jamming signal. Okay, so what happens is that if you send out a strong signal from this jammer, the received signal is likely to be like this, with this actual target signal being buried inside the signal. Okay, so the echo is not known, or you cannot extract this because it gets masked. So signal processing techniques can be used to detect this. So one solution is to do this. So you put one small antenna near the main antenna. You receive this signal from the jammer. You also receive a very weak signal from the target, but somehow this jammer signal is strong. So you use this auxiliary antenna and try to reduce the effect of this interference. Okay? So that is called adaptive noise cancellation or side lobe cancellation. The idea why it is called a side lobe is the antenna pattern has a main lobe, and these are called side lobes. Okay? So when you want to concentrate energy and you want to radiate, you will not be able to get a very sharp pencil beam without these things based on the Fourier transform properties. Okay. So this jammer tries to enter this whole system using the side lobe, so it is called a side lobe cancel. Dr. Ramakrishna here knows that he has built many of those systems. So this is a MIMO system where signal processing is used in trying to mitigate the effect of interference. The next system which we all are familiar with is basically wireless communication. All of us have cell phones, all of us use internet at home, and you would have seen some boxes at your home where there is a modem with a DSL phone line modem and two antennas sticking out like this. Correct? Now, what exactly are these antennas and what do they do? What happens? Why do we need two antennas? And are there multiple antennas in your phone? right? We don't know what it is. So this is called MIMO wireless communication, which has actually revolutionized the way we are able to generate high-speed internet data text. So what exactly happens is that in your home, when you have this, so these two antennas receive this wireless signal, let us say, from, this is a, okay, so there are two boxes here. One is called a Wi-Fi router and a smartphone, and one is a LTE 4G router. So let's go to the simple case of Wi-Fi. So what does Wi-Fi do? Wi-Fi router has multiple antennas, and your smartphone nowadays has multiple antennas sitting in your phone. You're not able to see them, but you can actually, if you open up the smartphone, there are multiple antennas. Now, why do I need multiple antennas in order for us to communicate? Okay? So the idea is like this. So let's assume that you have one antenna and one antenna. Okay? So you transmit a signal coming from one antenna. This antenna receives, and that is how the previous generation phones were. You have one antenna and you have another antenna, and you are able to communicate. So as the number of users keeps increasing, it is like you are no longer so many channels to use. Okay? So it is like, suppose I am talking, and now multiple people from the audience start talking. So what would happen? There is interference, correct? Because all of us are using the same band of speech band, right, or acoustic band from 0 to 20 kilohertz, right? So that audio band, multiple people start talking, you cannot understand what is happening, right? So if I have more and more people talking and using the same band, because my bands have been exhausted by users and I want to serve more and more users, then all I need to find out whether I can use one more antenna and see whether I can separate these signals using the same band. Okay? So to come to this example of whether if suppose two people are talking at the same time, is it possible for me to separate these two people, or two or three or four in the same band? So one way is that, can I find a signature or a signature of this person's speech such that I can separate them? So what is common here? The band, right? So the band is the same. But you are talking from another point and I am talking from another point. So suppose I have a system which will point a beam, an acoustic beam, towards where you are speaking and where I am speaking. The spatial signature is different for each of them, because you are talking from a position x1, y1, z1. I am speaking from x2, y2, z2, and using that, is it possible for us to separate them? Similarly, in communication also, if we use signals being transmitted on the same band, is it possible for me to receive it from two different antennas and try to separate them? So it's like two people are talking on the same band, two receivers are there, and somehow I will try and see whether I can separate them. Okay? So this is what is done in your Wi-Fi wireless communication router. Similarly, this 4G LTE router. Now, by placing two different antennas, how do I separate these signals? Unless the signals received by them are different, correct? So what you do is you do some testing, like a physics experiment. You take two antennas and you transmit from one point and see whether the signal received from each of these antennas is the same or different. Okay? So if you conduct that experiment and compute what is the signal power received from two antennas, and if you look at distance in meters or time in seconds, you will see that the response of the signal is different for these two antennas, okay, at a certain point. So in your phone right now, there are multiple antennas in smartphone. I will show you a small PCB diagram. And the signal received at each of these two antennas is different. So like this, right? So this signal received by this antenna is different from signal received by this antenna. So what is the advantage of this signal? So if this signal is low on antenna 1, and if the signal on this blue antenna is high, that means I am able to combine them to get a strong signal. Correct? So, if you don't have two antennas and you had only one antenna, then it's possible that when the signal is low, you are not able to decode the signal, or you are not able to receive the signal or interpret the signal. But if I am able to see that just a few centimeters away, I am able to get a stronger signal, then if I combine these two signals, then I can do a better job of receiving that signal. Okay? So this is just an example of an experiment which was done. So let us assume that this is your 2G signal, that is not the 3G signal, 2G signal, that is GSM. GSM we are all familiar. So suppose I listen to a GSM base station and I take my receiver and I walk along the wall of a house. Okay? Suppose you take your phone and you walk along the wall of your house, receiving the signal from your base station. The signal received on your phone will actually, if this represents a relative power in dBm, you will see that the signal goes as you walk. So this is what you would have observed, that if you are talking and walking, suddenly sometimes you will see that there is a drop in signal, or the call is dropped, or you are not able to hear properly. That is because the signal gets reflected from all the surrounding buildings, trees, etc. That is called multipath effect, and they can add either constructively or they can add destructively, and the signal level can fall almost about 30 dB. So you look at 160 and this is 190, so 25 to 30 dB is the signal can vary. So your receiver, your phone receiver has to be designed in such a way that you don't get your calls disconnected even when the signal is so low. That means your phone has to handle a huge dynamic range, a very strong signal and a very, very weak signal. So how do you do this, right? So if you take two antennas and look at the signal, it is quite likely that when this signal from one antenna was low, the other antenna signal could have been higher. So intelligently combining these two signals would be allowing your phone to keep the call on. But if it is too weak, then the call gets dropped, which we all encounter when we walk. So there are two things. One is that if you are not getting a signal which is not strong enough, you should walk a bit. Okay? It is quite likely that the signal will be stronger when you actually walk. This is a signal where at the same point in space, if I send two different frequencies, the signal which you receive at the receiver has two different strengths. Okay? Because two different frequencies can add constructively or destructively in a different way based on the environment. So these are all MIMO systems. So you should be very happy that there is a signal processing system which is actually able to extract these weak signals and make your phone work. It's a challenge. Wireless communication is a really challenging subject where signal processing plays a role. So this is what is inside of your smartphone. Okay. So your smartphone has, this is a Motorola 4G phone, and if you open up your stuff, this is the PCB, you can see that there is one antenna here and there is one antenna here. Okay. So these two antennas, and there are multiple antennas, there are other antennas for Wi-Fi, for LTE and so on and so forth. The reason why they are on the either side of the board is because the signal received by antenna 1 and signal received by antenna 2 are completely different signals. Okay, at the frequency of operation. Okay. You all know that if the frequency increases, the wavelength increases. So the spacing between these two antennas can be such that they can fit on a phone and you can receive signals which are different. So you will be able to combine signal from here and signal from here and ensure that you get a strong signal. Okay, so that is what we. So a simple signal processing technique would be pick the signal which is strongest. Okay, so that is just selection of an antenna. So whichever signal is strong, you sense it, pick it up, send it to your receiver chain, and then you can decode. But that is not a very intelligent or smart way of doing signal processing. So you can do many more using complicated algorithms. The other kind of MIMO systems are the audio signal processing algorithm. MP3, right? All of us have at least heard our music on MP3 on your phone. So MP3 is nothing but you take a signal, you are able to compress it. So initially there was no MP3, you would have required a lot of storage of your audio phone. So what exactly is the signal processing behind MP3? So what it does is it takes a signal. When you sample the signal using a sampler, it generates a lot of samples. So in speech and in audio, there is a lot of redundancy. So when there is redundancy, you can put a model to it, a mathematical model, and say that I will try to extract that model parameters such that I can reduce my information representation and then send that information which is of less rate or less quantity or whatever we call it, and it requires less storage. And then you have to decode that on your phone or whichever. So that is MP3. Speech recognition also requires a lot of signal processing. So let me show you what happens when you have microphone array. So suppose you want to have a robot in your home which will respond to your commands. And you want to talk to a gadget or talk to a machine. So we need to talk. If I want to talk to somebody or to the robot and ask the robot to come and do some task for me, then the robot should know where I am speaking from. Correct? Where I am speaking from. One way is to have cameras and say that, okay, this is where is the location. The other way people are building are called microphone array systems. So you have microphones on this robot, and using the direction from which the signal is coming, using these microphones. So each microphone will pick up the signal at a different level based on the location. Using that, you can ensure that you have a microphone array can tell you where you are, and you can use that information for the robot to come towards you. So these are just examples of systems. The other example of a MIMO system is called audio scene analysis. So suppose you are in a conference room and you are going to be talking and you want to know who has spoken what in that meeting. Okay, so that is called speaker diarization. That means you want to create a diary of all people, whoever has talked in that meeting. You would like an automatic minutes of the meeting. Okay, each person is talking. So that is possible only if you are able to find who has spoken what. Because all of them are going to speak in the same band, correct? But each one has a certain signature, either their voice signature and their location signature. So what you do is you create a microphone array, you put it on a table, you also put a camera, and then you try to capture signals from each one of them, and then separate them and do a speech-to-text recognition and then create a diary or a minutes of the meeting. Okay, so this is called audio scene analysis using microphone. The other thing where signal processing is used is hearing aids. Okay, so as we grow older, we are likely to wear hearing aids, and there is a lot of signal processing which happens in hearing aids. So what happens is that a signal is, so when you want to transmit a signal of a higher intensity into your ears, so you first receive the signals from the environment, somebody is speaking to you, you will have two microphones on your hearing aid, then you will have something called a sampler, analog to digital converter. You will do some signal processing algorithm, so this is analog, you digitize it, you process it, you enhance it, you do a DQA, give it to a small receiver, and that receiver, the speaker gives you the signal which you can hear. Now, I do know that these hearing aids are very simple to draw the diagram, but they are very, very poor in actual practice. Many of them complain that it is not natural. The hearing aids do not provide you natural hearing. They are very synthetic, or they are computerized stuff, right? So there is lot of research which is happening where you need to do a better job of understanding what the signal is coming, where the signal is coming from, and trying to see how to do that. Okay. So the other kind of MIMO biomedical systems are, this is an ECG machine. All of us have seen this at some point in time. So this is an ECG machine which has multiple leads. So this is also a MIMO system. Our whole body generates multiple signals from different parts of the body, and you can pick up these electrical signals and process and then try to find stuff. Then you have an EEG, electroencephalogram, which also has multiple inputs, multiple outputs, and you will get an EEG, and this is a fMRI scanner where you can scan and then find this. So all this is just examples of MIMO systems which affect our daily lives in some sense. We encounter them repeatedly on a daily basis. So, but what I will do is, I will try to take a few examples of how these systems can be used for our applications. So I understand that Mr. Anurag Kumar is going to talk about IoT, etc. when he gives a talk. So I will maybe do that. So I will now come to experiments carried out in IISc for building some interesting stuff. So one example is, can I classify a car of different size? That is, I take a Maruti 800, I take a Hyundai Accent, or I take a lorry or a truck, right? Now, is it possible for me to classify this while they are on the road without a camera? Okay. So the idea is that whether we can use a magnetic signature of each one of these vehicles, which hopefully we can provide it to an algorithm which will help ease our traffic problem. Okay. I'm not so sure if we can solve it, but the other example is, which I would like to show, is indoor positioning using inertial measurement units. So we like to use Newton's law of motion and see whether we can position somebody walking inside a building. So I will explain to you what we do. So the motivation for classification of vehicles is for road traffic management. Okay. So road traffic management is basically, you would like to know how many vehicles have gone are traveling maybe near a traffic junction, vehicle count. You want to know the traffic flow speed, and then you also want to know the occupancy, meaning in a road. So suppose there is a traffic light and you see 20 cars, and you would like to know, and at another junction, in the same traffic light, another road, maybe there are 10 cars. Right now our traffic system in Bangalore is that every traffic light has a fixed duration of red to green, right? But that may not be an efficient way of solving the problem of traffic, correct? So you should be adaptively changing our traffic lights so that we can send out the traffic in one direction. Currently, if you want to find the number of vehicles crossing a traffic junction, there is something called an induction loop. So the road is dug out, there is an induction loop. So when this metallic vehicle moves over it, it reduces the current and voltages, etc. And then you basically have to detect how many cars have passed. Okay, you won't work with bicycles and other things, but cars are generally. And there are other video cameras also are placed to count the number of things which the traffic police uses. But then for video cameras during night time it is a bit tough to, unless they are well illuminated, to count the number. So the other possibility is to see whether we can use a magnetic signature of a car. So what do we mean by a magnetic signature of the car? So suppose you have a magnetic sensor next to, let us say, a speed breaker, and whenever, so what happens is that the Earth's magnetic flux is reasonably uniform over a certain area. Now a metallic car moves into this magnetic field, or moves, when it moves, the magnetic field changes. So maybe I have a better diagram. Yeah. So this is the one. So let's say the magnetometer is here. There is an Earth's magnetic field. There is a cartoon description. The car is approaching. Okay. So when the car starts approaching and is closer to the sensor, the magnetic fields change. Okay. So the number of lines passing through this car will change, and this whole the sensor will be able to see something which is different than what you would be if it is normal. So the flux lines bend away as the vehicle crosses the sensor. So typically this is how a magnetic signature will look like. So let's look at this. So this is a car, an alto car. When it passes over the magnetic sensor, will have this variation. A Indica car will have this variation. And then the Maruti SX4 and the Sonata is an old car, right? So these are different variations. Now, once you are able to look at these signatures, is it possible for us to classify based on these signatures whether it is an Alto or a Sonata or an Indica, right? So one can do that. So first you create a database. So you get the signatures from various cars of different kinds, type 1, type 2, type 3. You collect all this, and then we use something called machine learning algorithms. So machine learning algorithms will try to detect patterns of all Indica cars signatures, and try to form patterns of all Alto cars, to try to form another classification, and then using some modeling technique, you try to extract the parameters of each one of them, and then see whether you can classify the signal. So there are techniques, there are various algorithms, and if you use one of these magnetic algorithms, so you get about 80% classification for a certain small car and a large car. So this is just an example of how signal processing can be used to find out which car is it. Now how useful is it, etc. will depend upon where it will be used in a traffic management system. Okay? Just to show that this can be done. Now this is an activity which I would like to go through in slightly more detail. So indoor positioning. So let me explain the scenario of what we pose. So indoor positioning basically for a first responder system. So let us assume that you have a building which is under attack, or there is a fire in that building. So what will happen? There is a first responder commando team or a first responder team which enters the building. Now since there is fire, etc., there is no infrastructure, there is no power, there is no Wi-Fi, there is nothing there. You enter this building using the team. So there will be a commander outside. Okay, so there is a command station outside the building, and then there are responders who go into the building. Now this commander needs to know where the team members are inside the building. Okay, they need to know where the team members are inside the building, so that they can communicate and plan, because different people go to different floors. Now we have GPS signals coming in, but they would not work well inside the building. We know that GPS doesn't work inside the building, but if you go outside, you get a good strong system. So how is it possible for us to find the location of these people when there is no Wi-Fi, there is no GPS, and you are just going there inside? The commander wants to know where the team members are. So that is the problem which was posed to us in that. So the first responder team will be given some sensing devices. They will have communication devices, etc. to talk, but they will not be able to tell, because if there is smoke, etc., you can't really find where your position is. So the idea was to see whether we can use our fundamental laws of physics, okay, of motion, Newton's laws of motion, and see whether we can use that to find out where I am in that building. Okay, so So the idea was that, okay, so let's look at a first responder positioning system. You have an RF-based positioning. You will have different sensors. So let us assume that we have inertial measurement units which you are put on your shoe. Okay. Now you wear that shoe with a sensor inside and you walk. Will you be able to find out where you are? Okay. It's a where am I question. Okay. And this is a MIMO system because you like to know, you get signals from various stuff and you get position, velocity and angle or direction where you go. So if you want to find your position, we need to understand what is the frame of reference. So if I wear a sensor on my body or even if I wear something in my wrist, so this is with respect to my body frame has a certain position, relative position. But this also has a relative position with respect to this room, right? And this room has a relative position with respect to the earth. So there are different frames of references. Now each frame of reference will have, if you want to find the position with respect to my body, and if that position is sort of given to you in terms of absolute positions of earth, then I have to do some transformation, correct? For which I need to know where, how I am moving, etc. So this is called the navigation frame and this is the body frame. And there are different motion, right? You roll, pitch, you can go like this, you can go like this. So what happens if I place an accelerometer and a gyroscope on your, or in a package, which is called inertial measurement unit? All smartphones now have this because you know when you rotate it, you suddenly get your picture in a landscape mode or a portrait, right? So typically, this inertial measurement unit will have 3 accelerometers and 3 gyroscopes. And this gyroscope will give you rate of change of angle, and accelerometers will give you rate of change of velocity. So this inertial navigation system can be built. So what is this inertial navigation system? It has been there for 40, 50 years. It is there on all ships, on planes and vehicles, moving vehicles, etc. But can I take that navigation system and put it on my shoe? Okay, so that's a question we can ask. So the inertial navigation system block diagram is you have an accelerometer, you have a gyroscope, and the gyroscope gives you rate of change of angle. If I integrate with respect to time, I will get the angle, right? Angle quadrant. Similarly, if I integrate the acceleration, I will be able to get the velocity, correct? So before that, this acceleration is on the body plane because I am wearing the accelerometer. It is on my body. So if I do like this, with respect to my body, I am generating some acceleration. But it will not tell you what is the acceleration with respect to the navigation plane. Okay? So I have to do some transformation for which I need to know some angles. So let's assume that you need to do some matrix multiplication of the vector. So I get this acceleration with respect to navigation because I want to know in this room where I am. Okay? Not with respect to my body. So this acceleration, of course, using the gravity model, this Coriolis force will not come into play for low velocity platforms. And if I integrate, I get velocity. If I integrate, I get position. So I get position, I get velocity, and if I take this, I get angle. So this looks very simple and everybody goes home, nice, comfortable. But what you need to realize is, this sensing mechanism, right, has to detect the acceleration accurately. So suppose you have a certain force you apply on this accelerometer, the acceleration which you sense, if the sensor is not of good quality, so you can see that there will be a true acceleration plus some error. Now that error is propagating through one integration, two integration. Correct? So suppose there is a acceleration which is true acceleration plus some error in acceleration. And this error in acceleration gets integrated once, that means it grows linearly, and if you integrate it twice, it grows quadrant. Plus there is this error in gyroscope which gets fed. So in some sense, this error is actually growing exponentially. So you make a small error in acceleration, measuring the gyroscope value, the error in position grows this time. So it can even grow in about 50-60 seconds, 80 meters error. So how do we control this growth of error? While the equations are all fine, what is a signal processing idea which you should think about? Okay. So if somehow you are able to find some reference points, then it is possible for us to control this growth. Okay. So that reference point is called zero velocity instances while walking. So now suppose you have this accelerometer on your shoe and you start walking. Every time your foot comes in touch with the floor, the velocity of your shoe is zero. Correct? Your sensor may say that it is not zero because of the errors. But you know that it is zero. So is it possible for us to give that feedback to your shoe module saying that your velocity is zero, but your algorithm is saying it is not zero. So is it possible for you to correct it? Okay? So to check that growth. And you can basically see that while you are walking, you will have some signals exist and you should detect that zero velocity. So you have different signals which come out, and these are instances of zero velocity. That means my stride when I walk, in about 60 seconds you can see, or in 10 seconds you can see that you have about 10. So every second I am putting my foot down. So can I use this information to find out or to control the growth of this error which is there because of this? So this is where we use what is called the Kalman filter. Okay? Kalman filter is a filter which is a signal processing algorithm which tries to reduce the error in terms of estimation. So you have an IMU, that is inertial measurement unit. You have the navigation equations, which is that block what we studied, that means whatever we saw, so there is integration, etc. happening. And then somehow if you are able to find the zero velocity detector, give it to this Kalman filter. This Kalman filter will try to take that input from the navigation equations or give it to the navigation equations to correct it. So this is a block of signal processing which requires a lot of, let us say, processing using matrix theory, etc., and estimation theory, probability theory, and to come up with this definition. Unfortunately, Professor Kalman passed away yesterday at the age of 86. He is living in Zurich. He passed away on yesterday. So, okay, so now you have all the mathematics all figured out, you have done some simulations. How do I build this and put it in a shoe? Correct? INS systems are usually quite large. So, is it possible for us to actually build something and put it in your shoe to find your position? So, the idea was to see that, yes, it is possible. So, this is a device from a company called Analog Devices, which has inertial measurement unit. That is 3-axis accelerometer, 3-axis gyroscope of very high quality. Then you build a microcontroller. This is called from a company called Atmel. This has a processor sitting on this board, and it has a floating point unit. It can do all those equations of the Kalman filter operation, matrix multiplications, inversion, and so on and so forth. And then you have a USB interface so that you can connect your shoe to a device. Okay. So what I will quickly do is, so this is what we built. We put everything into this module, and this module goes into the shoe. Okay. So this is what was done. And then you write software to run this whole stuff using training. So the first prototype is that you have what we call a small embedded platform. This embedded platform is a DSP board. And this DSP board is hardware platform. You can run your program. Okay, you can run your program on it. And then this shoe is connected to a USB, and this fellow uses a Wi-Fi, and it connects to a computer. And the computer will display my position of where I am while if I am walking with this shoe. So if you start, so this is a sample trajectory which we use. So we start at this red point, we walk, go like that, go like that, go like that in a big hall, come back and come back to the same point. But here you can see, I do not know if all of you at the back can see, there is a gap between the starting point and the stopping point. That is the error which incurs because your accelerometer gyroscopes are not able to sense the exact acceleration. The other thing you will notice is that this is like shifted, right? It is not exactly the trajectory which is there. So these are the errors which you need to check. This is another example of a student walking in a hostel. So you sort of start here, you climb down the stairs, walk, climb up the stairs, come back, and if you look at the scale, 0 to 1 is about a meter accuracy. That is, you incur an error of about a meter, half a meter, and you would like to have an accuracy of about a 1 meter for you to know that you are within the building. You are not. So, if these errors are to be controlled, the idea was to see whether we can build something which on both feet. Suppose right foot has an IMU, left foot has an IMU, and you start walking. Each one will be independently giving you the position of X, Y, Z. But this independent position should be such that it cannot go several meters away, because we know that our stride cannot be more than that, right? So we sort of built a left IMU and a right IMU, you machine and you do this. So let us say you have, this is the true trajectory which I am supposed to do it, traverse in a corridor, and this is what happens. You actually walk along this black line, but one shoe gives me a trajectory like this, the other shoe gives me a trajectory like this. Obviously this is not acceptable, right? I mean, it is completely wrong. So, but if you do a combination of these information, it is possible for us to correct to a certain extent. Still there is a problem of stuff. So it's like this, okay? Two shoe trajectories. So you can go like that, you can go. While you actually walked on this black path, the errors in the IMUs can give you complete errors. So this is where your signal processing thing has to step in and say, how can I correct this? How can I make this proper, right? So you sort of look at, you have a left foot, the right foot, when the right foot goes away, and it gives you an estimate which is far away from the left foot, because you know that your stride length cannot be greater than some value, right? You are not jumping, or you don't have extendable legs suddenly. So if you use this constrained optimization problem, saying that the distance between the left and the right foot estimates of your navigation equation should not be more than certain value, then you can sort of control the growth of error. So that is what is done in an optimization. Okay. So let me show you the trajectory which so this is an animation of a trajectory of a person walking in our department. So you start, you walk, you climb up the stairs. So you are climbing the stairs, going along a corridor. You're coming back, walking along another corridor on the same floor. Then you take the stairs at the other end of the building, come back, and you come back to, there's one more corridor, you go back and then you come back to this position. Okay? So this is a comparison of two methods, so don't worry about it, just assume that you have one. So this is the, so using your signal processing algorithms and the error management, you will be able to get the trajectory back. So this is a real-time system which is there. Now let me show you one video. It sort of summarizes this work.
Mercy on us.
shoe mounted or inertial navigation system, it goes into the shoe. The shoes are made in Shivajinagar. This was a joint effort between scientists and students from both universities together. Those are the shoes. Also wearing a helmet with a webcam and is walking. And you can see on this screen video of the person when they are walking in the so this is the right foot and the left foot. He is walking on ground floor. Then he will go up the stairs. When he goes up the stairs, this line will go up. You can see this is the z-axis, x and y. So we wanted to test this on Swedish firefighters. Okay. These are the Swedish firefighters. And they wore the shoes and this USB, and then they have a phone on which you can see the trajectory, okay, using Wi-Fi. Initially, what they have to do is they have to walk along a straight line to calibrate the sensors. Okay, they need to calibrate the sensors. And then we simulated as if there was a fire, smoke, on. And this is what the firefighters were doing. And this is what you can see. These two firefighters, as they walk, real time we get a position of the firefighters. Tablet or phone or whatever. So you are climbing the stairs. This is the climbing stairs. So I'll conclude by this. The IEEE Signal Processing Society calls signal processing as the science behind our digital lives. So that is what signal processing is all about. It is everywhere. We encounter it every day, every moment of our lives. And so it's a fascinating field to work, and it can create things which are essential for our comfortable living.